Hello, this is Nico, and in this Science with Nico we are going to take a look at addition polymerization in greater detail. This video is a companion to an earlier video, the introduction to polymers. A link to that video is now appearing on the screen if it is useful for you to have a look at that video. Alright, addition polymerization is super important. Polymers made by addition polymerization are perhaps the most common type of polymer that is used, and one of the things that is to be mindful of is that pretty much all polymers made from crude oil, which is a lot of them, are made by addition polymerization. So this is a method of manufacture of polymers that covers many of the plastics which we encounter every day in our lives. So let's start by taking a little brief look at the typical example for addition polymerization, and that is the polymerization of ethene. Here what you can see is we have monomers at the top, our individual small molecules that act as building blocks to our longer polymer chain. All right, of course, just here we're looking at this with a bit of a short polymer chain, but it's all we can fit on the page. Now, here, these monomers, the important thing to note is they have a double bond. You see that? You're looking at an addition polymer. All right, and the reaction that's going to be taking place is addition polymerization. And what's going to be happening is they are going to be reacting, that double bond is going to be opening up, and these monomers will be joining together one by one at a time to form this long chain. The big question, of course, is how? What are the specifics of that process? In this video, we're going to take a look at how these polymers are built using two different methods: free radical polymerization and the Ziegler-Natta catalyst reaction. Okay, but before we do that, it's challenge time. Okay. All right. Right now, the idea behind this is I go through the question, you hit pause, give it a go yourself at home, hit play, and I'll go through the answer with you. All right. So the challenge before you is for you to draw the structural formula for the following monomers: chloroethene, propene, and ethenylbenzene. So just remember, hit pause, give it a go yourself at home, and then when you're ready, hit play and I'll go through the answer with you. Alrighty, how'd we go? So let's take a look at these answers just here. Our first monomer, chloroethene, also known as vinyl chloride, has the following structure. Again, it has that all-important carbon-carbon double bond, and this monomer has one of its hydrogens replaced with a chlorine atom. All right, our second monomer is propene. We have a look here again, that all-important carbon-carbon double bond that enables it to actually react together, and it has one of the hydrogens replaced with a CH3 methyl group. And of course, the big daddy of our polymers, ethenylbenzene, here again, we have that double carbon bond, but in this case, off that monomer unit is an aromatic ring, what is known as a benzene ring. And that's a ring that essentially contains 3 double bonds. All right, except it's not 3 singular double bonds. They kind of spread out across the ring, and effectively, each one of these bonds acts like 1.5 bond. All right, it's a super stable organic structure, and this monomer is also known by the name styrene. Okay, let's get into looking at free radical polymerization. First off, we have initiation to look at, and initiation involves the use of an initiator to start our polymer reaction. So this is a class of compounds that is used by polymer chemists to generate a free radical to start free radical addition polymerization. Now, for our purposes, a free radical is a reactive molecule on the prowl for another electron to complete the valence energy level in one of its atoms. Basically, you can think of it as a molecule where a covalent bond has been broken in half and left the molecule in two separate fragments where only one electron from the pair of that covalent bond is on each fragment. So essentially, it's a small molecule with an unpaired electron. This makes it very, very reactive and tends to mean that out in the wild, in the environment, they don't tend to last too long. All right, so they tend to be something that only happens under specific circumstances. Now, in the case of our example here, dibenzyl peroxide, this is a common initiator used to start free radical polymerization reactions. And what happens is if we expose this molecule here to heat or light, this oxygen-oxygen bond in the middle here will break apart and give two free radical fragments. Okay, so let's take a look at how that actually happens. So if we pump in some energy, basically some heat or light, what happens is our initiator will break apart into two separate free radical fragments, which will then go on to interact in our reactor with our monomers of our polymer to start off the growth of our polymer chain. All right. Now, one of the things to be mindful, of course, is that this is a pretty sizable small fragment, okay? But let's take a look at how exactly it's drawn. The important thing is this little dot right here, okay? And that little dot signifies an unpaired electron. So that's the important point. But the actual structure here is not really that important for you to know, all right? And the reason for that is because polymer chemists commonly use a simplified symbol to represent an initiator, because overall, it's important that it exists. It's important that it's actually used to start the reaction, but there tends to be options in what we can do, in which type of initiator we use, and so the exact structure tends not to be so important at this stage. All right, so what polymer chemists tend to do is they do tend to actually represent an initiator using shorthand. Specifically, they represent it as an I with the free radical dot beside the I. Now, you need to be super mindful if you use this abbreviation yourself, okay, because I on the periodic table is iodine. So if you do use this in a written exam, make sure that you avoid confusion by including either a key or a label for your use of the letter I with a dot beside it to represent an initiator. The free radical, once it has been generated, then, when exposed to a monomer, will collide with the monomer and cause the double bond in the monomer to open up and send one electron to this carbon here and another electron to this carbon here, which will interact with the unpaired electron of the initiator, which will then join on to our monomer, creating a new free radical at the end of the far carbon of the monomer. This then starts the next stage of the free radical polymerization reaction, propagation. The new radical just here will continue to grow as it collides with more monomer particles, all right, during the propagation stage. Now here, the radical will actually interact with new monomers, okay, by having the unpaired electron here cause the double bond in the monomer to open up, sending an electron to each of those carbons like before, which will then cause the formation of a new covalent bond here, which corresponds right here on our new radical that's actually formed, and move an unpaired electron to the other end of the monomer, which preserves our free radical. And what will happen is our growing chain here will grow by 2 carbons at a time with each monomer it collides with. And it will continue to grow as more monomers are available, One of the things to note is that there's actually quite a lot of art involved in setting up your polymer reactions to control the growth of the chain during this stage. And so, with that said, this will repeat itself over and over and over as monomers are available and will cause the chain to grow to quite a considerable length. Now, there is one last stage to look at, the final stage of the polymerization reaction, termination. All things must come to an end. And in this final stage, notably called termination, what happens here is when two growing chains with a free radical at each end come together, what happens is those unpaired electrons at the end of each chain interact and they form a new covalent bond between the two growing chains, which causes the formation of our long polymer chain, effectively potentially doubling the size of our polymer chain, although not always. There's quite a lot of variation in the possible chain length that can happen. Alrighty, let's take a look at some of the features of free radical polymerization reactions before we move on to another challenge. Okay, so the free radical process involves a fairly large degree of randomness. Specifically, if we take a look at this type of reaction, because each of the steps of the reaction, initiation, propagation, and termination, are dependent on the random collisions within the reaction vessel, the molecular weight, and by extension the polymer chain length, can vary considerably. Okay, now a considerable amount of work has actually been done by polymer chemists to optimize their polymerization reactions and find the exact right conditions so they can control the degree of polymerization of individual monomers within the reaction mixture. But the one thing of note is, because there's going to be multiple chains and each of these chains is going to go through an initiation, a propagation, and a termination process, they're not all going to start at the same time, they're not all going to terminate at the same time, and they're not all necessarily going to grow at the same rate. There is going to be a difference in the distribution of polymer length, okay, as we look at the number of chains in a polymer. Now, what that of course means is that if we were to look at any polymer by molecular weight or even chain length, it's going to vary. Alright, the second concern to have when looking at free radical polymerization is chain branching. Okay, now imagine the following scenario just here, okay? So we have the middle of a growing polymer chain, and along comes a second growing polymer chain, and it runs right into the middle of that chain. Now, what will actually happen here, and it can actually happen to one chain by itself if it curls back on itself, is the growing chain with the free radical will actually interact with the covalent bond between a carbon and a hydrogen on the middle of the other chain. Now, this will cause the hydrogen to be ripped off that chain to terminate this growing chain right here and create a new radical at the middle of a chain while terminating the other growing chain. Now, from this radical here, of course, as it runs into more monomers, a new growing chain can start. And so in that way, what can happen is you end up with a second chain branching off from the first chain. Now, that's a major factor in free radical polymerization that tends to happen quite a lot because the whole process is reliant on random collisions between particles. Okay, so there's a degree of disorder, and any polymer chemist, if they make a polymer by free radical polymerization, will expect a degree of branching in their polymer chain. And that will in turn affect the final properties of the chain. Alrighty. Challenge time. Here I have another question for you to complete at home. Alright, the challenge this time is for you to draw the 3 stages of the free radical polymerization of the monomer chloroethene. So, pause the video, give it a go, and when you're ready, hit play and I'll go through the answer. Just remember, at home, you should give this question a go. So pause the video. Alrighty, let's go through that answer, okay? So, in our first stage of our polymerization of chloroethene, we have initiation. Okay, so here we're using an I with a dot beside it to represent our initiator as just a type of shorthand, just to keep things nice and simple. We have our chloroethene molecule. Notice again the important double bond and the chlorine atom. Okay, so when the initiator meets this monomer, what happens is it causes the double bond of this monomer to open up and send an electron to each of the carbons, which causes the free unpaired electron of the initiator to form a new covalent bond with the monomer and moves the free radical to the other end of the carbon chain. This then starts the growth of a growing chain. It's only small at the moment, but as it runs into more monomers in the reaction mix, what happens is that growing chain, the free radical at the end of it, causes those monomers double bonds to open up and give an electron to each of those carbons in the monomer, which again causes the formation of a new covalent bond, joining the 2 new carbons onto the growing chain, along with actually moving the free radical to the end of the growing chain. Alrighty, and that'll repeat over and over and over as more monomers come into contact with the growing chain, until of course it meets another growing chain, in which case it undergoes a process known as termination, where the 2 chains will come together and the free radical of each chain will interact to form a new covalent bond between the 2 carbons at the center of the chain, causing the formation of our polychloroethene polymer. Alrighty, that's the answer to our challenge. It's quite involved this time. Okay, let's take a look at the Ziegler-Natta catalyst reaction. This is the second type of polymer reaction that we're going to be taking a look at. And this second reaction involves a series of steps that are actually, it's quite a bit more complex than the free radical process. It was discovered by 2 scientists. I think we can figure out what their names were. All right. And it is especially useful as a polymerization process because it can make polymers that can't be made by free radical polymerization. Okay, it can make polymers that are linear. That means they're a straight, unbranched chain. Okay, and it can also control the orientation by which monomers actually connect to the chain. In contrast, free radical polymerization tends to give only branched chain polymers that have a degree of randomness to how monomers actually attach to each other across the chain. Now, the process by which the Ziegler-Natta catalyst reaction takes place is actually really complex, and it's above what you need to know at this stage when it really comes down to it. But we can actually simplify this for our purposes, okay, and look at what we really just need to know, okay, because it's important to be able to contrast this to free radical polymerization. Now, if we consider our catalyst for our Ziegler-Natta reaction to quite simply be an end cap at the end of the chain, we can actually describe it as a titanium chloride complex that essentially acts as like this cap, this end piece on the end of the chain that actually controls the growth of the chain. So what happens is it actually controls the addition of new monomers to that chain. And so that causes that chain to grow, right, as new monomers are actually added to that. And because this process is not happening by random collisions, it's actually controlled by the catalyst, it tends to be really quite the controlled process, and that gives us a great deal of control over what's going on in the reaction, and that lets us create a range of really unique polymers, all right? And for example, that lets us create block copolymers, such as the one pictured here, where if you have a really close look, there's actually two different monomers in this chain. We have 2 units of chloroethene and 2 units of propene in our block copolymer, and by having them grouped together in blocks, we can actually create some really interesting effects when it comes to the behavior of the properties of our polymer chain as that actually interacts with things like solvents. Okay, and of course we can also, even to the great degree, control the orientation of rings. So for example, if we take a polystyrene polymer just here, okay, and we can use the Ziegler-Natta catalyst process to actually control the orientation of monomers as they come into join the chain. And so that actually lets us control whether or not the benzene rings, and this is a different way of drawing benzene rings, it's a little bit simpler than the fully expanded structural way I have been drawing them. All right, it lets us control what side of the chain that they're on, and that'll affect the final properties of the chain in terms of the hardness and crystallinity of the polymer chain, as well as things like how flexible it is and so forth. You can have them all on the one side or have them alternating. All right, and that's really quite a special thing. Okay, so by having that degree of control, we're able to actually create some really unique polymers that let us, for example, really control our polymer chain. Now, that sounds absolutely great. The Ziegler-Natta process sounds wonderful in the point that you can control the orientation of the monomer, you can control the degree of branching in the chain, right? And specifically, you can have unbranched chains, which you can't have from free radical polymerization. But the Ziegler-Natta process does have some of its own limitations. Specifically, it has a great deal of difficulty in working with some monomers. All right, for example, chloroethene is very, very difficult to work with a catalyzed reaction to actually control that polymer. All right, and that's owing to the point that during some of these catalyst processes, and the Ziegler-Natta process is one of several catalyst-controlled polymer reactions. All right, they can generate a radicals during the catalyst process, which can start free radical polymerization of the monomers that you are trying to react with your catalyst in a controlled way, which obviously poses difficulties. All right. But at the same time, the Ziegler-Natta process offers this great versatility and control, so it still finds use. All right, let's wrap this video up. All right, in review. Okay, we've taken a look at two different polymerization processes. Specifically, we've taken a look at the free radical polymerization process that involves three stages: initiation, propagation, and termination. We've also taken a look at catalyzed polymerization reactions, specifically the Ziegler-Natta polymerization reaction. And we've simplified that by representing the catalyst as an end cap on the end of the polymer chain. We have noted the features of the polymers produced by each of these processes. Specifically, free radical polymers tend to have a degree of randomness to the length of the chain, which will cause the molecular weight and resultant chain length of the polymer to occur as a relatively sizable distribution across the polymer chains. And they also have a tendency to be branched. In contrast to this, polymers produced by the Ziegler-Natta process tend to be unbranched. They also tend to have a high degree of control in how the monomers react with the growing chain, which controls the orientation of the polymer, and specifically controls the orientation of the monomer as it attaches to the polymer. In addition to that, they are of great help when creating copolymers. Those are polymers that actually involve a mixture of two different types of monomers. Alrighty, that's a wrap. Thanks for watching this video. I know it has been a long one. If you have any questions, feel free to comment below, or you can catch me in class. Alright, bye.